Welcome to day one of our deep dive series on AI large model training and inference. Today, we'll explore the fascinating journey from raw text to intelligent responses. This session will provide a step-by-step walkthrough of how large language models work, transforming vast amounts of data into meaningful insights. Whether you're new to AI or looking to deepen your understanding, this series will guide you through the essential processes involved. Welcome to this guide on mastering large model principles for your career. Many candidates claim familiarity with these concepts, yet struggle with practical questions like how to prevent error accumulation during training. In this guide, we'll explore key areas: inference mechanisms such as autoregression and teacher forcing, data processing, including tokens, BPE and vocabulary, sampling strategies like stride and batch size, and architecture design, covering embeddings, transformers, and output structure.
Welcome to Part 1, where we'll explore the inference mechanism behind large language models. These models are designed to generate text by predicting one word at a time. Essentially, they analyze the context provided by preceding words to determine the most likely next word. This process continues iteratively, allowing the model to construct sentences, paragraphs, or even entire narratives that are coherent and contextually relevant. Let's dive deeper into how this fascinating process works. Welcome to the concept of autoregressive generation. Imagine typing a sentence like, "The weather is nice today," rather than generating an entire paragraph at once. The model works like a typewriter, producing one word at a time. It uses the previous words to predict the next. This loop of input, predict, append, and repeat, is the core of autoregression, where each word depends on those that came before it.
Let's talk about the end token. This special token is what tells a model when to stop generating a response, much like a period signals the end of a sentence. Without it, the model would just keep going indefinitely. But it's not just a technical feature. It's a learned behavior. The model must understand when a thought is complete. So if you're asked how the model knows when to stop, remember, it's all about the end of sequence token.
Today, we're diving into the key difference between training and inference in language models. Think of training like an open book exam, where the model sees the correct answers as it learns. This is known as teacher forcing. In contrast, inference is a closed book exam, where the model must rely solely on its own predictions. Understanding this distinction is crucial for anyone working with large language models, as it separates basic users from true experts.
Let's explore how the model learns through loss and backpropagation. Imagine the model predicts, "certainly," "very suitable," instead of the correct, "indeed," "very suitable." The system calculates a loss value for each word, averages them into a total loss, like 0.3, and then uses backpropagation. This process adjusts internal parameters, refining predictions, much like a teacher guiding a student to play an instrument correctly.
Welcome to Part 2 of our presentation, where we dive into the fascinating world of data processing. Here, we explore the journey of raw text as it transforms into a format that machine learning models can understand and use. We'll discuss the crucial steps involved, such as tokenization, normalization, and encoding, to ensure that the data is clean and structured, making it ready for model consumption. Welcome to From Texts to Tokens. Computers don't understand sentences the way we do. They work with numbers. To bridge this gap, we break text into tokens, which are the smallest units of meaning for the model. For example, the sentence, "The weather is nice today," becomes 5 tokens. Each token is then assigned a unique numeric ID, creating a model-ready input. This transformation allows the model to process language effectively.
Today, we're tackling the out-of-vocabulary or OOV problem. Traditional tokenizers often stumble on words they haven't seen before, like XGBoost, which can disrupt the entire meaning of a sentence. Enter Byte Pair Encoding, or BPE. It breaks words into meaningful subunits, allowing even unknown words to be understood. BPE offers two major advantages. It preserves root semantics, such as im and un, and it assembles new words like building with Lego blocks. Welcome to part 3 of our presentation, where we'll delve into our sampling strategy. This is a crucial step in machine learning, focusing on how we slice, package, and deliver training data to the model. By efficiently managing these processes, we ensure that the model receives diverse and representative samples, which are essential for its learning and performance. Let's explore the techniques and considerations involved in optimizing this aspect of our workflow.
Today, we'll explore sliding window sampling, a powerful technique in text processing. By slicing a long text into numerous input target pairs with a sliding window, we create training examples where the target is the input shifted one token to the right. This enables the model to predict the next token at every position. Essentially, this method turns a single paragraph into thousands of informative examples, maximizing the value extracted from each sentence for training.
In this slide, we explore the concept of stride in data processing, focusing on balancing overlap and diversity. A small stride, like one token, provides dense coverage by capturing every token context, but risks overfitting due to high repetition. Conversely, a large stride, such as 3 or more tokens, offers greater generalization and diversity, though with less coverage per text unit. The takeaway? Use a large stride for big datasets and a small stride for smaller ones to optimize results. Let's dive into the concept of batch size, focusing on its impact on parallelism and stability. A batch consists of multiple input target pairs processed together by the GPU. The batch size is simply the number of samples handled in each forward pass. Larger batches can speed up processing by optimizing GPU utilization, but they come with trade-offs. They offer smoother average loss for stability, but require more VRAM, impacting memory usage. Welcome to Part 4, where we explore the model architecture pivotal in transforming numbers into language. We'll dive into the 3 core layers that make this possible. These layers work together to process numerical data and convert it into coherent and meaningful language. Understanding these layers is crucial for grasping how language models function, enabling machines to understand and generate human language. Let's take a closer look at each layer and its role.
Let's explore the embedding layer, the first step in transforming text into something a model can work with. Here, each text token is converted into a high-dimensional vector, like a digital ID card. These vectors capture semantic meaning, grouping similar words together. For instance, cat and dog are close in this space, while apple is much farther away. This process enables the model to compute language, bridging words and mathematical analysis.
Let's dive into Layer 2, the transformer layer, which acts like the brain of the model. Through multi-head self-attention, it captures relationships between any 2 words in a sentence, no matter how far apart. Each word evaluates its relevance to others. So sweet in apples are sweet connects with apples. By stacking many transformer layers, models refine understanding, grasping not just structure, but also emotion and implicit meaning, unlike RNNs. Welcome to Layer 3, the output layer. At this stage, a fully connected network transforms the final transformer outputs into a probability distribution across the entire vocabulary. Each possible next word is assigned a score. The model then picks the next token based on these probabilities, advancing one step in the autoregressive generation process. While structurally straightforward, the output layer plays a crucial role in selecting each word you see in a chat response.
Welcome to the complete architecture pipeline. We begin with the embedding layer, which transforms discrete tokens into continuous semantic vector representations, essentially turning language into math. Next, the transformer layers utilize multi-head self-attention to capture global context across all tokens simultaneously, enabling a deep understanding of the input. Finally, the output layer converts these refined representations into next token probability distributions, driving precise word-by-word generation. Welcome to Everything Connected, the full picture. Think of data as the fuel, where BPE tokens and sliding window samples nourish the learning process. The architecture acts as the engine, with embedding, transformers, and output driving understanding and generation. Training is all about fine-tuning, using teacher forcing, loss, and backpropagation to enhance accuracy. Finally, inference is where value emerges, as autoregressive generation transforms learning into real-world solutions.